Good morning, students. I welcome you to the third session of mine on electrochemistry. In the last two sessions, we learnt about what are electrolytic cells, what are galvanic cells, and what are the differences between them, how to represent a galvanic cell, etc., etc. So, with our background, today we shall move on to discussion on what are reversible and irreversible cells, then derivation of Nernst equation. Nernst equation is used to calculate electrode potential as well as to calculate EMF of a given cell. Then the standard hydrogen electrode, which is called as a primary reference electrode, its construction and working. And if time permits, let me speak about the calomel electrode also. Right. So these are the topics which I am going to cover in this third session of electrochemistry. So what are reversible and irreversible cells? So let us consider reversible cells. Once we understand the concept of reversible cells, it is easy to understand what are irreversible cells. So the simplest way of understanding the meaning of a reversible cell is, if a cell reaction can be reversed, the reaction taking place in a cell, if it can be reversed by some means, then that cell is called as a reversible cell. Right? So a reversible cell in a real sense can be considered as the one in which the cell reaction can be reversed. You will understand it later. And as I said in the last class, a reversible cell consists of two reversible electrodes, because any cell requires two electrodes for its construction. Because single electrodes are of no use. We require a pair of electrodes to construct a cell, and a pair of reversible electrodes, when coupled or when joined, forms a reversible cell. Right. So I said a reversible cell in simple terms can be considered as the one in which the cell reaction can be reversed. Okay. So to know whether a cell is a reversible cell or not, we can identify by combining that cell to an external EMF. The cell under consideration has its own electromotive force. So by connecting it to an external EMF, we can identify whether the given cell is a reversible cell or an irreversible cell. So to know whether the given cell is a reversible cell or not, we connect it to an external EMF. So when E external is equal to E cell under consideration, because to know whether the given cell is a reversible cell or not, we connect it in a circuit to an external EMF. So when external EMF is equal to EMF of the cell, no current flows either from the cell or from the external EMF to the cell. So whenever external EMF applied is equal to EMF of the cell, neither current flows from cell under consideration to external EMF, nor current flows from external EMF to the cell under consideration. This is the first condition. So whenever applied EMF is exactly equal to EMF of the cell under consideration, no current flows in the circuit. Number 2. If external EMF is less than EMF of the cell under consideration, because we are testing whether the given cell is a reversible cell or not. So when external EMF is less than EMF of the cell under consideration, then current flows from the cell to the external EMF. So current flows from the cell to the external EMF. In a sense, cell reaction takes place in forward direction. And you'll understand when I take up a particular example. So when external EMF is less than EMF of the cell, then current flows from the cell to the external EMF source and cell reaction occurs in forward direction. Third condition, when external EMF is greater than E cell, if the applied EMF is more than EMF of the cell under consideration, then current flows from the external EMF to this cell. Now, under these conditions of E external being greater than E cell, the cell reaction occurs in backward direction. Here, when E external is less than E cell, cell reaction takes place in the forward direction because cell reaction is taking place and current is produced, and that current produced is passing to the external EMF. On the other hand, if applied EMF or external EMF is greater than EMF of the cell, then current flows from external EMF source to the cell under consideration, and now the reaction of the cell occurs in backward direction. So when these three conditions are satisfied, then the cell is said to be a reversible cell. So, and if a cell does not satisfy these conditions, or for a given cell, if these conditions, three conditions are not applicable, then such a cell is called irreversible cell. So therefore try to understand what is a reversible cell. Then it's easy to understand what is an irreversible cell. So we learned that a reversible cell follows the following, the earlier three conditions we discussed. And examples of reversible cell is your best thing is your mobile battery, because every day you charge it. When you use the mobile, the cell is producing current and that energy is utilized by your cell phone. And when you keep it for charging, the cell reaction takes place in the opposite direction and the cell reaction is reversed. Therefore, best example is your battery used in cell phone or any rechargeable cells. We have dry cells of two types, rechargeable and non-rechargeable. So all rechargeable dry cells are reversible cells, and the cells which cannot be recharged, which are to be thrown when EMF falls to zero, are irreversible cells. So usually the cells that we use in torchlight may be reversible or irreversible. They may be chargeable or not chargeable. So all chargeable cells are all chargeable batteries. Because battery is a set of cells. A series of cells when connected becomes a battery. Right? So a cell which can be recharged is a reversible cell, and a cell which cannot be recharged is irreversible cell. So the quartz cells that are used, or button cells that are used in your wristwatches, are the best examples of irreversible cells. Once your watch stops functioning, we throw away that and insert a new cell. Therefore, the quartz cells used in your wristwatches are the best examples of irreversible cells. Also, the quartz cell used or the button cell used in our calculators are also examples of what? Irreversible cells. So, all chargeable cells are reversible cells, and the cells which cannot be recharged are irreversible cells. This is the simplest way of understanding a reversible cell and an irreversible cell. Right. Now let us consider an example of a reversible cell, which you already learned in your 12th standard, or I also considered this Daniel cell example in one of my earlier sessions. So Daniel cell, which is a galvanic cell, is an example of a reversible cell. This is a reversible cell. So what is the cell reaction taking place in the galvanic cell? That's Daniel cell. This is the reaction taking place This is the reaction taking place in the Daniell cell. So when we are drawing current from the Daniell cell, zinc is oxidized and copper ions are reduced. Zinc loses electrons and forms zinc 2 ions. Copper ions in the solution take up electrons, then get reduced to copper. So this reaction occurs in forward direction when the cell is in use. When you are using the cell, in the sense when you are drawing current from this cell, forward reaction is taking place. Right. Now, if this cell is connected to an external EMF source, and if this cell is connected to an external EMF source and external EMF or applied EMF is greater than EMF of the Daniell cell, then what happens? Backward reaction takes place. When the cell is used to draw the power, zinc is getting oxidized and copper ions are getting reduced. Now when the EMF of this cell falls to 0, we cannot draw the current. So now EMF of this cell when falls to 0, we can connect it to an external EMF in such a way that external EMF is greater than EMF of this cell. So then when external EMF is greater than EMF of this cell, what happens is reverse reaction takes place. So zinc 2 ions are reduced to zinc and copper is oxidized to copper 2 ions. So whatever the reactants have been consumed in the forward direction during power consumption from the cell, and when EMF falls to 0, what we do is we connect it to an external EMF. So that external EMF is greater than the EMF of this cell. Then what happens is that products are converted to reactants. So we get back zinc in the solids form and the copper 2 ions in the aqueous form when we connect this Daniell cell to external EMF, and external EMF is maintained at higher values than the EMF of this cell. So this cell reaction is reversible. Therefore, this is one of the examples of a reversible cell, because here the cell reaction can be reversed. So you take any galvanic cell made up of a pair of reversible electrodes, then it is always a reversible cell. So a reversible cell is always made up of a pair of reversible electrodes. And when the cell cannot be recharged, when the cell reaction cannot be reversed, then we call it as a irreversible cell. So this is how we can differentiate between reversible and irreversible cells. Now let us consider Nernst equation. So Nernst equation enables us to calculate electrode potential as well as EMF of the cell. Theoretically, we can calculate electrode potential of any given electrode and also EMF of any given cell. That is the importance or significance of Nernst equation. So Nernst equation enables us to calculate EMF of the cell or electrode potential. So this derivation is important. So if we consider a cell reaction of the type, I am considering a general cell reaction. Whenever I write like this cell reaction is a reversible one. Alright? So if we consider a general cell reaction of this type, AA plus BB gives us to CC plus DD, where A is number of moles of A, B is number of moles of B, C is number of moles of C, and D is number of moles of D. Right? And equilibrium constant for this reaction, as you already learned in your 12th standard, is written by this expression. This is the expression for equivalent constant of this reaction, because we are considering a reversible cell reaction. Now, from thermodynamics, we can write expression for change in free energy of this reaction. So change in free energy is given by expression delta Z is equal to delta Z naught plus RT natural logarithm K, where K is, in some books they start with Q. Q is reaction quotient. Expression for reaction quotient is also the same. The difference between Q and K, both this is reaction quotient and this is equivalent constant. Both reaction quotient and equivalent constant have same expression. The only difference is K, which is equivalent constant, has got a constant value at a given temperature under a given set of conditions. K is a constant under a given set of conditions, whereas reaction quotient is a variable. The moment a reversible reaction starts, in the beginning reactants are converted to products. After some time products start reacting, giving back to reactants. So what happens, till the equilibrium is attained, there will be difference in the rates of backward and forward reaction. So because of the difference in rates of forward and backward reaction, till equilibrium is attained, there will be change, continuous change in this ratio. Because rate of forward and backward reactions are different, so there will be continuous change in the concentration of this when the reaction is taking place. And once equilibrium is attained, rate of forward reaction would be equal to rate of backward reaction. So under the conditions of equilibrium, this ratio remains constant. That's why it is called equilibrium constant. So for any other situation other than equilibrium, this expression denotes a reaction quotient. So reaction quotient is a variable, whereas K, that is equivalent constant, is a constant. That's why it's called as a equilibrium constant. Right. So in some books they start with Q, then replace it by K. I am directly using this. So delta Z, the change in free energy for this reaction can be written as delta Z is equal to delta Z naught plus RT natural logarithm K, log base E K. So where delta G is change in free energy, delta Z naught is change in standard free energy. When I say standard free energy, under standard conditions of temperature, pressure and concentration. R is a gas constant, universal gas constant, 8.314 joules per Kelvin per mole or 2 calories per Kelvin per mole, or it could be 0.0821 liter atmosphere per mole per Kelvin. So there are different values of R which are studied in states of matter and a gaseous state. So here we use 8.314 joules per Kelvin per mole. And T is a absolute temperature. In physical chemistry, we always express temperature in Kelvin. Okay, we use Kelvin scale of temperature. So, and this K is a equilibrium constant. And we also know that delta G is equal to minus NFE. This is another derivation which we do not derive, we simply assume. So delta G can be related to EMF of the cell or electrode potential by the expression delta Z is equal to minus NFE, or we can also write this as minus delta Z. Both mean the same. So decrease in free energy is represented by minus delta Z, which is equal to NFE, where E is the EMF of the cell or electrode potential, F is the Faraday's, which I learned in again second 12th standard. 1 Faraday is equal to 96,500 coulombs, the approximate value, because Faraday is the charge carried by 1 mole of electrons, and it's less than 96,500 coulombs, slightly less than that. But for all practical purposes or calculation purposes, we take F equal to 96,500 coulombs. This is the charge. So charge means Faraday is the total charge carried by 1 mole of electrons, right? And so F is Faraday, N is number of electrons involved in the cell reaction. It could be 1, 2 or 3. So N is number of electrons involved in cell reaction or number of electrons involved in electrode reaction. F is Faraday, which is constant, equal to 96,500 coulombs, and E is EMF of the cell, or it can also be considered as electrode potential, as the case may be. So delta Z, minus delta Z, or delta Z is equal to minus NFE. Similarly, delta Z naught is minus NFE naught. So I said standard free energy change means we are fixing the conditions of temperature, pressure, concentration, etc. So delta G naught is constant, whereas delta G is variable. You should remember that. E is variable, E naught is fixed because we are fixing the temperature, concentration and pressure. So delta G is equal to minus NFE naught. So these are the thermodynamic expressions. So substituting these values. So let us take this as equation 1. So substituting the values of delta Z and delta Z naught, we have minus NFE is equal to minus NF E naught plus RT log base E T. And this is equation 2. Now dividing equation 2 by minus NF, dividing the equation by minus NF, we can write this expression as E is equal to E naught. Because we are dividing the entire equation by minus NF, this becomes minus RT over NF log base E. No. Log base E can be converted to log base 10 by multiplying with 2.303. And since K value already had written, you can write this as E minus 2.303 RT over NF log the general equation that we considered. Capital C to the power small c, capital D to the power small d. Try to remember because you have. Okay, this is the expression. So we have minus sign here. When you put minus sign here, you have products in the numerator and reactants in the denominator. We can also rewrite this expression like this by putting plus sign. We can also, so this is where most of the students get confused. So absolutely there should be no room for confusion, because we can put minus sign here or plus sign here. If you put minus sign in the Nernst equation, products will be in the numerator, reactants will be in the denominator. If you put plus sign here, reactants will be in the numerator, products will be in the denominator. So absolutely there should be no confusion. Right, this is a Nernst equation. So this equation can be used to calculate electrode potential or EMF of the cell. This reaction is further written in some books as E is equal to E naught minus 2.303 RT over NF log of reduced state by oxidized state. This is also another expression which is nothing but the other form of this. If you put plus sign here, oxidized state by reduced state. Right. So this is a Nernst equation, and substituting the value of R as 8.314 joules per Kelvin per mole and T at 28 degrees, that is 298 Kelvin, and F is equal to 96,500 coulombs. This equation, so 2.303 into 8.314 into 298 divided by 96,500 approximately comes to 0.0591 by N log of reduced state divided by oxidized state. So this is the basic form of Nernst equation. This is very, very important. Once we know the way it's derived, it's very easy to remember this expression. Because equations should not be remembered, you should also know how to derive. When you know the derivation part and when you understood the concept, it's very easy for you to write down the equation on your own. Right. So now, if you apply this Nernst equation, calculation of electrode potential. I said Nernst equation is used to calculate electrode potential as well as to calculate EMF of the cell. So if I noted down this, we'll see how to apply this Nernst equation to calculate electrode potential. So in general, if we consider an electrode reaction of this type, it's a metal, I'm considering metal ion electrode. So, and we always consider as per IUPAC convention, reduction reaction. Okay, reduction reaction is to be considered. I have told you in the last session that according to IUPAC convention, we use only reduction potentials. And when I say electrode potential of a particular electrode is 0.5 volts, it means without any ambiguity that I am mentioning reduction potential. So unless they say oxidation potential, it is only reduction potential. So whenever I say electrode potential means it is only reduction potential. Or whenever you come across the term electrode potential of X is so much, then it is only reduction potential. If you are mentioning oxidation potential, if you are using oxidation potential, then that will be specified. Right. So according to IUPAC convention, we use a reduction process. Right. So now this is the electrode reaction. For example, like zinc electrode. This is the electrode reaction taking place at zinc electrode. When zinc rod is dipped into zinc sulfate solution of particular concentration, that serves as a zinc electrode. So you can write this expression, Nernst expression for this. E electrode is equal to E naught electrode minus 0.0591 by N log. Since we have a minus sign here, we write the products and reactants in the denominator. And you have learned in your PUC under chemical equilibrium or in 12th standard under chemical equilibrium that the molar concentration of pure solids and pure liquids is taken as unity. So the pure solids and pure liquids in a reversible reaction do not appear in the expression for equilibrium constant. So we write like this. Okay, or if you change this to plus sign, 0.0591 by N log of Mn plus. So this is the Nernst equation for electrode potential. So if you want to write this Nernst equation for zinc electrode, so you have, I erase this. So E of, I said in Rossler, if we represent like this, it's the reduction potential is equal to E naught Zn2 plus Zn minus plus 0.0591 by 2 log of Zn2 plus. So this is the expression for electrode potential of zinc electrode, and this is the Nernst equation for electrode potential of any electrode. Right? So this is how Nernst equation helps us in calculating electrode potentials. Now if you consider an electrode of this type, So calculate electrode potential of this copper electrode. So copper rod is in contact with 0.1 molar copper sulfate solution. E naught of copper is 0.34 volts. So how to calculate electrode potential of this electrode? We know the Nernst equation. E electrode is equal to E naught electrode plus 0.0591 by n log of Mn plus. This we know, right? Now you substitute this in this equation. E naught electrode is how much? 0.34 volts plus 0.0591. What is the number of electrons involved? Copper 2 plus ions are converted to copper by accepting 2 electrons. The electrode reaction here is copper 2 plus 2 electrons. This is the electrode reaction. So number of electrons involved is 2 log of 0.1. 0.1 can be written as 10 to the power minus 1. Log 10 to the power minus 1 is minus log 10. Log 10 is 1. So this becomes 0.341 minus 0.0591 by 2. So by simplifying this, you can calculate electrode potential. Okay, so it's very easy to calculate electrode potential using Nernst equation. Now we can also calculate EMF of the cell. For example, if you have a acid reaction, again let me take Daniel cell. So calculate EMF of this cell at 25 degrees Celsius. Concentrations of copper and zinc are given. E naught cell is given. So how to calculate EMF of this cell? So E cell is equal to E naught cell minus 0 or plus, you can put anything, 0.0591 by 2 log. So now in order to write expression for K, you should know what is the cell reaction. This is the cell reaction. Okay, so I have put plus sign here. Means reactants will be in the numerator, and zinc metal is a pure metal. Its activity will be 1, so that does not come into picture. And on the product side we have zinc. So E naught cell is 1.10 volts plus 0.0591 by 2 log of copper ion concentration is 0.1. This is 0.01. Or we can also write this as log of 10 to the power minus 1 by 10 to the power minus 2. Upon simplification, this becomes log 10. Log 10 is 1. So you have EMF of the cell equal to this. It's very simple. So this is how we can calculate the EMF of a cell also using Nernst equation. Because of time constraint, I'll consider more and more examples. You can watch my video repeatedly and try to understand the use of Nernst equation in calculating electrode potentials as well as EMF of the cell. Then you can solve problems on your own. Take any electrode, zinc electrode, copper electrode, silver electrode, right? Fix any concentration. You take concentration of the electrolyte of your choice. Try to solve. That's how you have to improve conceptually, right? Then, the next topic here is standard hydrogen electrode. So in the last class, we learned that it's impossible to determine single electrode potentials. As said, single electrodes are of no use, like 0. 0 without any digit on its left side has no value. Same way, a single electrode has no value. It's of no use. Only when you have pair of electrodes, then we can construct a cell and we can do some useful work. So in order to determine electrode potentials, when no electrode potential is known, how to determine electrode potential of any other electrode. So in order to determine electrode potentials of different electrodes, scientists needed a reference electrode, means an electrode whose potential is known. When no electrode potentials are known to us, then how to solve this problem? So in order to solve the problem of determining electrode potentials, scientists considered standard hydrogen electrode as a reference electrode. And this standard hydrogen electrode is shortly abbreviated as SHE. It is abbreviated as SHE, right? Standard hydrogen electrode. And this is called as a primary reference electrode. I'll tell you later what's primary and what's secondary. So primary reference electrode. So what is this standard hydrogen electrode which is considered as a reference electrode? So the scientists considered standard hydrogen electrode as a reference electrode. Then they connected this SHE to the other electrode whose potential is to be determined in the circuit. And EMF of the cell is determined using a potentiometer. And EMF of the cell is equal to E cathode minus E anode. And here SHE electrode potential is 0. It is taken as 0. Remember this. So scientists considered SHE as a reference electrode and fixed its potential arbitrarily 0. So they arbitrarily fixed the electrode potential of SHE as 0. So it is only assumed. It is not determined because we do not have any choice. So SHE is taken as a reference electrode and its potential is taken as 0, and that is connected to another electrode whose potential is to be determined. So SHE with the test electrode forms a cell. Its EMF is measured using a potentiometer. So EMF of the cell would be equal to electrode potential because SHE potential is 0. Right? So standard hydrogen electrode is taken as a primary reference electrode and all other electrode potentials are determined using this. So what is this standard hydrogen electrode? We do have standard hydrogen electrode and simply hydrogen electrode. So what is standard hydrogen electrode? As I already come across, standard electrode potential, standard EMF of the cell means we are fixing the terms like pressure, temperature and concentration. Right? So when you fix these three factors on which electrode potential depends, electrode potential is also fixed. I said E is variable, E naught is constant because in E naught we are fixing the temperature, we are fixing the concentration, we are fixing the pressure. So E naught does not change. So also here, standard hydrogen electrode means pressure of hydrogen gas is fixed as 1 bar because now earlier it was taken as 1 atmosphere. Now even in NCERT books it is a standard pressure is considered as 1 bar. So temperature is 298 Kelvin. Concentration of hydrogen ions is 1 molar. So when these conditions of pressure, temperature and concentration of H plus ions is fixed, then hydrogen electrode so formed is called standard hydrogen gas electrode. So how is this standard hydrogen electrode is constructed? So hydrogen gas at a pressure of 1 bar is passed through 1 molar HCl solution at 298 Kelvin. So standard hydrogen electrode is constructed by passing hydrogen gas through 1 molar HCl solution at 298 Kelvin. So when these conditions are rigorously maintained, then only that hydrogen electrode serves as SHE. And if you change any one of these, it simply becomes hydrogen electrode. Right? I repeat, only when these three conditions are fixed, it is she. If you change any one of these conditions, it becomes he. This is how simplest way of remembering. Only when these three conditions are rigorously maintained, it behaves as she. If any one of these conditions is not maintained, then it acts as he. Right. So we have understood what is meant by standard hydrogen electrode. Then how is it constructed? So we have a glass tube of this fashion. And there is a hole here to pass hydrogen gas, and this is placed in 1 molar HCl. Temperature is maintained at 298 Kelvin. Then a platinum wire is introduced for making electrical contact because hydrogen gas has no surface. So an inert metal like platinum is required to make electrical connections. Okay, so this is the construction of what? SHE. So hydrogen gas at 1 bar pressure is bubbled through 1 molar HCl solution at 298 Kelvin, and a platinum wire is inserted to make electrical connections, and now this behaves as SHE, standard hydrogen electrode. And what is the electrode reaction that is taking place? 2H plus. It's a reversible electrode. This is the electrode reaction taking place. It's a reversible electrode. It can act as an anode or cathode. So it acts as cathode when connected to copper electrode. It acts as anode when connected to zinc electrode. I have already told in my earlier class the significance of sign of electrode potential, minus sign and plus sign. So let me not go into details of that. So this is the electrode reaction. But what is the electrode potential for this? It is taken as 0. So if any one of the conditions like pressure or temperature or concentration is changed, then electrode potential changes. And this is a standard hydrogen gas electrode. So its electrode potential is arbitrarily taken as 0. H2, H plus bar half H2. Or we can write like this, a reduction potential. So E naught of this standard electrode potential of hydrogen electrode is 0. So this taking the standard hydrogen gas electrode whose potential is assumed to be 0, all other electrode potentials can be determined. So let me stop here. I will continue in the next class, and please comment on my videos in the comment section. Thank you.